Namaskar, welcome back. So, this was the last discussion we had about the prediction of the earthquake, and as I told that there were few uh, successes where the earthquakes were been predicted and people were been saved. Okay. There is another example from Himalayas, from Indian side, where the earthquake was been predicted, and this was from northeast. Now, this area is having like it falls in zone 5 and it has the record of triggering many earthquakes. So, the earthquake sequence was been watched very carefully here for different periods, like for example 1897 to 1952, 1953 to 2001. And what it the observation was that there was no earthquake during the period of 1953 and 2000, almost like 50 years. No earthquake was been there of greater than or equal to 7.5. So, this was one observation, and then since this area is under high strain, so there was the concern that this area can trigger earthquake in this region. And in the past, there was an earthquake of 1897 Shillong Plateau earthquake. Magnitude was around greater than 8.5 or so. And then there were few reports on the paleoliquefaction. This we will come later about the liquefaction part, but ancient liquefactions were been seen in the alluvial plain areas, which also suggested that there is a recurrence of 400 to 600 years. Okay. Nevertheless, the seismicity which was been seen was for 50 years, but then also this was an important finding that great earthquake of similar magnitude like 8, okay, or 8.5, around 8.5 can have a recurrence of 400 to 600 years. But in between the large magnitude earthquakes can occur of 7.5. Okay. So, that was one part which was been taken into consideration, and then this was a successful case study of earthquake forecasting in northeast. So, global efforts towards establishing precursors. So, this was based on the precursor pattern that preceded the major earthquakes. Usually, we talk that about and the SWAM or quiescence time. Okay, if there is an sudden no seismicity has been seen and you have that period of quiescence. Okay. So, the area is sitting quiet. So, similar exercise was been done considering the sequence of earthquakes and the quiescence period by Gupta and Singh in 1986 and 1989 in the vicinity of the Indo-Burma border, where we recently had an earthquake along the Sagaing fault system. Now, this was an earthquake in 1988, and Gupta and Singh discovered one such region shown in the image which has been shown, and they also told that if our prediction which we are saying okay is not correct, then probably this is a false alarm. However, it turned a true alarm, and the forecast was with the parameters which we see here, that the epicenter was been given that it will be somewhere in this region, and the epicenter which was observed during an earthquake was this thing. Okay. And then they also highlighted that what would be the magnitude. Okay. So, they say that it could be 8.5 or around 8, but the earthquake of 7.3 took place. Okay. They also gave the depth, which will be around 100 plus minus 40, and the depth was 90.5 kilometers. Okay. And the earthquake which was been time which was been given for that was between February 1986 to December 1986, and the earthquake was after 2 years, that was in 1988. So, this was predicted, and such type of studies can help in predicting the earthquakes in future if we have close monitoring of the seismicity, ongoing seismicity. Now, coming to the part which is important again is the depth of the earthquake, that what we call at the location where the energy is released, okay, is subsurface, is known as your focus, and exactly top on the surface is your epicenter. Okay. And this displacement will take place on a fault plane. Okay. So, this is your fault plane you have. Okay. So, this is your fault plane, and the fault scarp, that is the surface manifestation, that what we usually identify in active tectonic studies. Okay. And the fault trace. Okay. So, if you put a trench here, this we will discuss later on, then you will be able to gather the information of the past earthquakes in this region. Okay. And one can also talk about the depth, as I told, that is also termed as focus or hypocenter of the region, and based on the occurrence of the earthquakes, okay, that is the main shock and the aftershocks. Okay. One can also decide that what was the fault area or the rupture area which was involved for triggering this earthquake. This is from Bhuj, 7.7 to 7. We can say 7.6 magnitude was the precise earthquake which was been assigned, that is the magnitude which was been assigned to this earthquake of 2001. And the area which you see was this much actually on the surface, you can see, because these are all pitch and ball diagrams, but it is showing your surface locations, that is your epicenters. Okay. Now, triggering stress, as I have mentioned in the last lecture, that the small part of stress are released which were accumulated slowly when the earth plate moved towards or past each other. Okay. Since the earthquake drops the stress or the accumulated energy on that particular fault which slipped, the earthquake will not recur until the stress is rebuilt. That is what we were talking about, the typical the Higgs plate diagrams. Okay. But this is not always true. So, it will take time, okay, to rebuild that much of energy. Okay. And that is what, and it may take, if you are expecting a larger earthquake, you need a larger amount of energy. Okay. So, it takes thousands of years or hundreds of years to acquire that much of energy. But an earthquake will occur elsewhere at the site other than the slipped fault. Okay. So, if you are having multiple faults, and if the energy has been released on this, okay, then you may say that on this fault it may not, this fault may not trigger an earthquake in near future, because it will require time to rebuild that much of energy. Okay. But this fault, which is also under stress, okay, may trigger earthquake in near future. So, the areas where the stress is building up will be the sites for the next earthquake to occur, both of large and small magnitudes. Okay. So, this type of expectations and the understanding helps that, okay, fine, now this portion has released the energy, or this fault line has released the energy, the next earthquake can be predicted on the another fault lines. Okay. So, there are instruments which usually are been used, but now we have very high resolution instruments which deployed in many seismically active regions, as including India. We get this information very quickly on our mobile phones. Okay. So, National Seismological Center, which is the part of the Ministry of Science, has an app, Bhukamp, which helps us in knowing the earthquake anywhere in the world. Okay. Anywhere in the world. So, this was a sort of an achievement which we had after 2001 Bhuj earthquake. Okay. The deployment of these instruments, that is what we call the seismograph, were been increased. Okay. And we have multiple seismographs sitting at different locations, and few are like very high resolution, which can record the earthquakes which is occurring anywhere on this earth on earth. Okay. Now, mostly what is been used is your very typical conventional method, and still this has been followed, but this has been done very fast, very quickly. Okay. In few seconds or maybe in the minutes, you will get the information on your mobile phones. Okay. So even on the emails, okay, you can register on the websites and of USGS or NCS, you will keep getting this information. Okay. Now, there are two or three different motions which one can observe during the earthquake, and the civil engineers, basically the structural engineers, are also keen in knowing this ground acceleration, what we call. Okay. So, one is the we can say the horizontal motion, and another is your vertical motion, because as we have learned in the beginning that seismic waves will have different type of motions. Okay. So, you have like which can move the land, push and pull, then up and down, sideways, elliptical. So, based on that, in particular areas, okay, the structural engineers and the seismologists, they are very keen in knowing that what was the ground acceleration in terms of the horizontal motion as well as the vertical motion, and that helps in building the codes for having a proper construction in the regions. Okay. So, this is, as I told, is the very typical conventional method, and this conventional method used the arrival time of P and S wave as well as the amplitude of it. Okay. So, difference between the amplitude and then you have the difference between the arrival time of P and S wave can give you magnitude on logarithmic scale. Okay. And this is what we call Richter scale. Okay. This has been, like as I told, that this is very fast and very quickly computed, and you will see the information coming up very fast. Okay. Now, one has to understand that the difference between magnitude 6 and 5, which has been shown here, okay, is like lot of differences there in terms of the energy released, and you cannot simply say that it was 5 magnitude or 6 magnitude. If you say 6 magnitude, then the amplification, and you can see in the seismogram that it is quite different than the 5 magnitude. Okay, the amplitude of the recorded seismic waves. Okay. So, an earthquake of magnitude 6 registered with 10 times the amplitude as an earthquake of magnitude 5 from the same location and on the same seismograph. Okay. So, same instrument showing a different, almost 10 times larger amplitude as compared to that is for magnitude 6 as compared to magnitude 5. Okay. That difference is an increase in 1 on the Richter scale. Okay. The horizontal axis on this seismograms is time, that is the time arrival, and the vertical is your ground motion. That is what we call amplitudes of that. Okay. So, one has to clearly understand that the energy level which has been seen or observed during the difference of 1 magnitude is very, very large. Okay. So, there are graphs or which are available which helps in identifying the location of the epicenter. Okay. So, minimum 3 seismograms are required to locate your earthquake. Okay. So, that is what the intersection of that will be your epicenter. So, locating the epicenter, if you see here, okay, so you have 3 stations, okay, which have been shown here, SOCO, then you have TEIG, and then another is SSPA. Okay. Now, all these stations are located far away in terms of the distance. They are not at the same distance from the epicenter which was been located. Okay. And also at the same time, you will see that the amplitude as well as the arrival time in the P and S wave is different. Okay. So, closest one to the epicenter, you see the arrival time, that is difference between the P and the S wave is pretty less. Okay. So, only 1.5 minutes, and the distance was around 900 kilometers from the point, or that is the epicenter, which marks the place or the location of maximum energy released. Okay. And then second, as you move away farther, which is around 1800 kilometers, the time difference is 3 minutes. Okay. And farther you go, like for example, the SSPA, then which was sitting 3300 kilometers, the time difference is your 5 minutes. Okay. So, this is one way which based on which the curves have been generated, and that helps you in identifying the radius of from the center, that is the radius from the location of your seismogram. So, difference in the arrival time between the P and S wave reveals the distance from the seismograph, okay, to an earthquake epicenter. This plot shows records from seismograph at different distance for a single earthquake. Okay. So, the intersection of this has been taken as an epicenter of the earthquake. Another question which remains is that sometime you do not see sort of an intersection of this at least 3 stations. Okay. So, more stations are been taken into consideration, and you will see a sort of a revised location of the epicenter. That is also very fast. Okay. In few minutes you will get that location. Okay. So, this is the same part you have, which shows the section of the earth, the crust, and the surface part. Okay, which explains that how the different seismographs will receive your seismic waves passage, and also again you need to keep in mind what we have learned about the P wave shadow zone and S wave shadow zones. Okay. Now, coming to the part where what type of faulting has occurred is also important. Okay. And this has also been done on a very faster way in using the softwares and all that nowadays, which gives you the sense of movement, okay, that how this faults and what is the sense of displacement in terms of whether it is a lateral displacement or it is thrust displacement or it is a normal fault, that one can identify based on this. Okay. And this has been done based on the arrival of first motion. Okay. So, first record of the wave, okay, that is the amplitude, will be taken into consideration. So, some stations will have positive amplitude recorded and some will be having negative recorded. Okay. So, these are the stations which have been shown with the black dots here, and each stations with respect to, for example, if you consider this as a fault line here on the surface. So, these stations which are sitting away from the fault have recorded different motions. Okay. So, first motion here which is positive. So, you have push away from epicenter. So, it is pushing away. Okay. Similarly, on the other side you have the first motion So, that also push away from the epicenter, and whereas here it pulls towards the epicenter. So, it is moving, the stations are moving towards the epicenter, that part is moving towards the epicenter. So, you will have a compression here, you will have an extension here, okay, and that will result into this portion moving this side and this portion moving this side, okay, and that results into your right lateral strike slip moment. Okay. You may also consider the other direction, where usually people takes or the scientists take into consideration whether that can be the option of the fault trace. Okay. So, for example, you are having the first motion of the P wave arrival in the seismograph stations is used to determine the orientation of the fault plane, okay, and the direction of the slip. So, whether it is the station are been pulled, if the negative waves are there, then pulled towards the epicenter. So, that is in compression, and then red arrows are showing your extension, they push away from the epicenter. Now, the case shown here, okay, of is the right lateral strike slip. Okay. Note that the alternative pattern of pushes and pulls would remain the same if the plane, that is the fault plane, you are having perpendicular to the rupture of that. Then in that case it will become left lateral. Okay. So, if you consider this one, then it will become left lateral. So, this will be the motion here, will be you will have this motion. Okay. So, there are both cases one can have, but once you know the trace on the surface, you can easily make out that what was the fault displacement. Okay. So, these are a few things which one can use to identify when the fault planes, this we call fault plane solutions. Okay. So, these fault plane solutions are been used extensively to identify the displacement, nature of displacement on the fault, okay, during an earthquake. And these are also termed as pitch and ball diagrams. Okay. So, for normal faults, you have this is positive, negative, and then you have for reverse fault, it has been shown like this, and whereas in the strike slip, it has been shown like that. Okay. Now, a recurrence of earthquakes due to stress development by tectonic forces. Okay. This part we have already discussed, so we will just move ahead, and then we will see about because this is the part which is connecting. Now, in 2001, the earthquake was triggered here in this area, and this is the map of Bhuj. We can see, you can locate based on this one here. So, Bhuj is located here in the Indian plate. So, this was 2001 Bhuj earthquake. Now, what we observed was suddenly there was an increase in seismicity in this area. Of course, this is the what as I told that this is the rupture area, okay. But we saw that there is an increase in seismicity along what we call Gedi fault. Okay. So, as I told that possibilities are high that the next big earthquake may be triggered along the Gedi fault, because there is a stress transfer on that area. Nevertheless, the stress is available, the energy is available on the Gedi fault also, and the 2001 earthquake has triggered the stress on the another fault. Okay. Now, classification of earthquake on the basis of focal depth. This is again important, and these are the basis on which the classification has been done. Okay. So, you have an upper plate earthquakes, but depth remains very shallow, up to 20 kilometers. Then you have thrust earthquakes, which goes up to 50 kilometers, and then you have inter-slab earthquakes, the areas where you are having subduction going on. Okay. And then you have like deep earthquakes, which goes up to 300 to 700 kilometers. Okay. So, we will discuss more on this in the next lecture, that how effective this shallow earthquakes and deep earthquakes are in terms of their effect, in terms of the seismic shaking and damage pattern and all that. Till then, thank you so much. Namaskar.